Okay, so hello, welcome everybody to the Statistical Physics Journal Club Talks. Today we have a joint talk by Santhosh and Subhadip from ICTS, and they'll be talking about Taylor-von Neumann-Sedov blast wave solution and the comparisons with microscopic simulations of a one-dimensional gas. So Santhosh will start the talk. Over to you, Santhosh.
Hello, good afternoon, everyone. Have a nice day. So, the topic of my presentation is Taylor-von Neumann-Simon blast wave solutions, and we compare with the microscopic simulation of one-dimensional gas. This is done in collaboration with Subhadip and Abhishek, and it's based on recent work of the same name. So let us start with the motivation and also explain the term Taylor-von Neumann-Sedov blast wave solution. So the interest in this problem has started since World War II, and this describes what happens after there is an explosion. So once there is an explosion, namely a burst of energy has been localized to in a small area. After an explosion happens, what happens? This is what the problem studies, and this has obvious consequences in World War II. And here we try to study what is so when there's an explosion happens, we have something called as a blast wave. So we try, there are some differences between a blast wave and a normal explosion. One of the main differences is that blast waves are developed in a much smaller space compared to a normal wave, a normal explosion. Because of that, the transmission of energy occurs at a much higher pressure. So when energy transmission happens from the bomb to the air, surrounding air, it happens at a much higher pressures in a blast wave when compared to a normal explosion. So that is why it is very devastating. And this one of the consequence of this is that a blast wave has a it has a shock front. So this is a shock front. I'll come back to that later on, because uh, there are many interesting features in the blast wave solution. One of them is the self-similarity of the solution in time. So I will also try to explain what is self-similarity later on, and let also try to give a like the blast wave solutions. One of the good feature of a blast wave solution, as I was saying, is that it has a very sudden shock front at the edges, and that would lead to a surface of discontinuity in quantities that we are interested in, such as pressure, velocity, and temperature fields. So this is a significant feature of a blast wave, and also the fact that it has a self-similarity solution in time. So Taylor-von Neumann-Sedov equations are the hydrodynamic descriptions of a blast wave. They study the blast wave as a point source production from the waves producing from a point source, and they study the evolution of these waves. Our current work is motivated by studying the blast wave propagation and the transport of blast wave in a one-dimensional hard particle gas. So a hard particle gas system is a system with particles which interact only through a perfectly elastic collisions, and they are point particles. Our model, the systems are point particles, and when the collision happens, the system velocities of v1 and v2 are transformed to v1 prime and v2 prime given by this formula. So the equal mass case when m1 is equal to m2 is very trivial, where by substituting this we get the solution which is solvable. But our problem, we are interested in the unequal masses or alternate masses. So here is the description of the outline of the talk. The first part, which I'm going to present, the hydrodynamic description, which closely follows Taylor-von Neumann and Sedov solution. And the second part will be talk will be given by Subhadip, where we try to compare what happens, the comparison of the hydrodynamic solution and the microscopic simulation. So without further any stoppage, let me start over to the hydrodynamic equation. Are people here? Am I audible?
Yes, yes.
Yeah,
Yes. Thank you. So let's start with the hydrodynamics. So the hydrodynamics of a system is well captured by Euler equations. So Euler equations describe how the profiles of the conserved quantities evolve with time. And Euler equations, what we see here are not exactly Euler equations. Euler equations are those where right hand side are zero actually. Uh, so del T rho plus del X rho V equal to 0 is the first equation, which is the conservation of density. The second equation, del T rho V plus del X dou V square plus P is equal to 0, is Euler equation which talks about the conservation of momentum. And likewise, del T rho E plus del X rho EV plus PV is equal to 0 is the Euler equation which talks about energy conservation. P here is the pressure of the system. For the hard particle gas, we consider in one dimension, we consider the system as an ideal gas. So it is given by PV, P is equal to rho T. We have taken the Boltzmann constant to be 1. It so happens that these equations are the hydrodynamic equations and they turn out to be the Taylor-von Neumann-Sedov equations in one dimension. And as they have done, what we do here, as you can see in the plot in the right hand side, we give a blast wave like initial condition where the energy is localized in a small region. It doesn't look very small. It looks like the width, it's a Gaussian, it looks like a Gaussian and the width is a bit big. That is because we wanted to make, if it is too narrow, we find a problem that we run into a problem that the hydrodynamic equations actually blow up because of the discontinuity, because of its jump. So on the one hand, we try to make the initial condition broad enough so that this blow up doesn't happen. On the other hand, we also make sure that it is not too broad. Otherwise, it will not be called as a blast wave initial condition. Hence, this is a blast wave like initial condition. So, if we take Euler equations without the terms on the right hand side and integrate, we run into problems.
Hello.
Yes.
Yeah, can you explain once again this? If it is too narrow, then what will happen?
If it is too narrow, the discontinuity we have del x term in the equation. Because of that, because there is a del x of some term, the jump will be very high, and that can lead to problems in the long time limit.
Oh, you're saying derivatives are too high.
Derivatives are too high. Yes.
Okay, okay, okay. Because I know there is no discontinuity. You can still have a continuous function which is narrow, but you're saying derivatives are too high, I guess.
Yes.
Okay, thank you.
Thank you. So when these Euler equations, if we evolve in using numerical methods, it is well known that a one-dimensional Euler equation blows up. And I will get back into to this a little bit more detail later on. But please accept for the time being that one-dimensional Euler equation blows up. So we need to add extra dissipation terms to keep this in order to stop this blow up problem. And this happens due to shock formation. So once there's shock formation and there's a blow up happens, so to counteract that, we add additional dissipation terms. In the second equation, in the del T rho V plus del X rho V square plus T term plus P term, we have added the dissipation as a form of a Navier-Stokes term. This eta is the viscosity of the system. And in the third equation, we add a thermal conductivity term, which is kappa is the thermal conductivity, and del xt, this is the conductivity term. So now what we have done is with the blast wave initial condition, with energy given by this uniform density and zero velocity, we have evolved this system and we find the following scalings, following solution, evolution, in fact. The bottom three panels, one can clearly see the evolution of the system. So the system at t equal to 100, we see that it
Sorry, can I
yeah,
ask you? Can I ask you a question? Can you go back to
please.
the equations?
Yeah.
Yeah. So kappa and eta, are those functions of x or anything else? And what is
Yes.
p?
Kappa, so the kappa and eta are not themselves constants, but we have taken it for a one-dimensional system. We have used some green Kubo formalism, and one can show that kappa is a function of temperature. Kappa depends on temperature as T power half. Similarly, eta depends on temperature power half, and kappa also depends on rho. There are some references where they have showed that kappa depends on rho as rho power one third. So we have taken kappa as rho power one third into T power half, and eta we have taken as uh, T power half. In addition, there are constant factors of order
multiplied by
one.
some constants.
Yes,
Multiplied
of
by some
order one.
constants.
Yes, of order
Of order
one.
one. And
Yes, so we have taken
P?
one actually. P is the pressure of the system, and it is the ideal gas. We have considered the alternate mass system as an ideal gas system. So P equal to rho T by mu, where mu is the reduced mass and T is the temperature of the system. Shall I proceed?
Okay. And this is one dimensional.
Yes.
Boundary conditions.
So what we have taken is that we are interested up to that point where the system reaches the boundary. So we have considered a periodic boundary condition system, and we are only interested up to the time the system hits the boundary.
Periodic with periodicity equal to what?
We have taken a system periodic in x, and we have taken a distance of x is around 2000, and we are interested in what happens until the system reaches the boundary.
Okay. And the method that you used to actually solve these is that?
Yes, I'm coming back. I'll come to that.
Oh, you're coming to that. Okay.
Yes, please. Yeah. So we can clearly see that these are the bottom panels. Three plots show what happens to the evolution at different times: 100, 200, 400, 800, and 1600. We can see the three conserved quantities rho, v, and t here. And yes, these equations have been solved using the McCormack method. This is a standard explicit way to solve a PDE, which is second order in both time and space. So the bottom panels show the evolution
Santhosh?
of. Yes, please.
Yeah, you said these are conserved quantities. Is it rho v the conserved quantity, not v?
Even v. I mean, we can analyze it in terms of v as well as rho v. It turns out v is also conserved here.
Oh, okay.
Okay, no, maybe I don't know if is it probably it's not conserved, but we can compute it. I think it's not conserved. Is it because it won't satisfy a conservation equation?
So that's what I was confused.
Right. Yeah. So it's derived from rho v, which is conserved, but it's not conserved. Yeah.
But
be honest,
rho
neither
is
is t.
conserved. If rho is conserved and rho into v is conserved, then v should also be conserved, right?
Not necessarily, because
not necessarily. It depends on the flux.
Yeah, it's if you look at the equation for v, it's not in conservative form.
V squared might be monotonically decreasing, but v is not integral v is not a conserved quantity.
Right. Yeah. Yeah, but anyway, this is just a plot of whatever field.
Right. I was just confused by the phrase conserved quantities. These are not conserved.
This top panel plots are density plots, and the momentum plots and temperature plot.
In the meanwhile, can somebody else maybe answer the question? What's the numerical method he was mentioning?
Hello, can you hear me?
Yeah.
Yes.
My connection got lost. It happens even in ICTS, so I'm sorry.
Okay, you can go on. Yeah, there was
So
a
what's
question.
question?
Yeah, what was the numerical method basically that you mentioned? I didn't quite catch.
I lost the signal for long time back. I see.
No.
We have used. So we have used a McCormack method. I can't share my screen. Can you guys see my screen?
We are seeing these old plots.
You can see my slides, no?
Yes,
Yes.
yes.
Thanks a lot. So we have used a McCormack method to solve this system of PDEs, and this is a second order method both in space and time. So using this McCormack method, we see that we have solved these three solutions. This is in the bottom panel, and in the top panel we see the scaling. We at different times we have scaled the x-axis and y-axis so that they collapse on each other to see if there's a collapse or not. While the collapse is very good for the velocity profile, it's not so good for density and temperature profile in the center. Otherwise, the collapse is good, but at the center, it seems that the collapse is not very good. Let's postpone that for the moment. Let's postpone the analysis. Let's hold on that for a moment. I'll come back to that very quickly. So now what we have just seen is that there's an x by t power 2/3 scaling in the hydrodynamic equations. Now the question is, what did TVNS Taylor-von Neumann-Sedov observe? In d dimensions, it was observed that the r of t, which is nothing but the radius of the shock front, it scales with time. The radius spreads, the shock front spreads in time as t power 2 by d plus 2 in d dimensions. Since this is a one-dimension system, we get r of t goes as t power 2/3, which is pretty much consistent with our solution. But let's try to derive, let's try to see, because we also have to scale the y-axis, so not just the x-axis. So let's try to derive this solution actually. That's what we have done. We have attempted to derive this solution. Generally, what we have done is we have chosen a generic scaling of rho, v, and e in terms of rho naught plus t power b, and v as t power c into v tilde, and e as t power d e tilde. So this entire system, we assume that the scaling in the x-axis is x in t power a. Now, basically, we are required to find the values of a, b, c, d. For the time being, we since we are doing some solution analytically, we neglect the dissipation terms and only consider the Euler equations. So we substitute the scaling solutions in the Euler equations, and we hope to derive the exponents a, b, c, d. We hope to derive the exponents as unique exponents, and we hope to recover x by t power 2/3 scaling. That is the aim. So what we have done is we did just that. We substituted these scalings in the Euler equation, and we get the three equations shown in this slide. These equations look very cumbersome, but the short story is that these equations have been derived from Euler equations. These equations have x and t variables. But what we have seen in the previous slide, was that there was a scaling in the x and y, in the scaling of the solution. At long times, we observed a scaling. If we observe a scaling, it means that we should be able to describe this system using a single variable and not two variables, x and t, but a single variable. Actually, we should be able to describe this in a single variable, x into t power a combination actually, because we are assuming that the x into t power a is the scaling solution. Hence, we demand, yeah.
Santhosh, sorry, one question. Uh, so this is so there is no eta and kappa. So where is the eta and kappa?
Because we have neglected the dissipation terms for the moment. So we will come back to the effect of the dissipation terms later on. We are only doing this analytically. So to analyze the scaling of the solution, eta and kappa will analyze their effect later on.
Okay. So can you go back to the three equations once? I just want to see.
Yeah. So we are only taking the left-hand sides and equating them to 0.
I see. Okay. Okay. Yeah. Okay. Yeah. Okay.
And these numerical plots, when you solve, do you have these dissipation terms?
Yes, we have the dissipation terms. Otherwise, I will come back to that. Please allow me, give me some time. I will come back to that with that question. We need the terms. I will show what happens if there are no terms. Please give me a few moments. May I proceed?
Yes, yes.
Thank you. So we have these three equations in terms of the scaling variable x t power a. Now what we are trying to do is we want to convert it into a single this equation in terms of a single variable x t power a. We don't want x, we don't want t, but we want x and t only in the combination of x t power a, which we are denoting by z. So what we have done is, in order to
One
yes, please.
quick how did you get a v cube term? From which term gives you a v cube?
Yeah. That is because
Rho v cube.
yeah, rho v cube comes from rho into E into V plus P into V, right? So P is pressure. Pressure is rho T by M, rho T by mu. I'm sorry. And T is given by, let me show you the slide. T is given, and E is given in terms of temperature in this way. There's a V squared term. That is why you get this. Can you see this equation E equal to V square by 2 plus T by 2 mu? Hello?
Okay. Yes, except
Yes.
that. Oh, wait. This has to. I don't understand the units of this. It means what happened to rho? Wait, v square by 2. How can that be e? What happened to rho?
Plus T by 2 mu also, right? Temperature.
Yes, but just the first part.
Yeah.
How come it's v square by 2?
Because
that's not energy density.
like generally this velocity, when you have velocity, this is the kinetic energy part, initial part, and the T by 2 mu part is due to the internal energy.
So that is the internal energy density. That is why.
Yeah, internal density. Yes.
So rho times E is the internal energy density. So if you multiply rho on both sides.
Rho E is the internal
equal
energy.
to rho
Okay,
v square, rho T and everything.
Okay.
Yeah. Okay.
Okay.
That's why we have the rho v cube part here. So now we demanded that there's only x into t power a in the whole equation and there's no other way. So thus every other place where we find x and t in the form of anything else other than x t power a, we demand it to be 0. We demand that the t term should not appear there. So the t power minus b, we demand that it shouldn't appear. That can only happen when the exponent is 0. Thus, we have equated the powers of t to 0 in all other places, and we find that we get a solution of b equal to 0, a plus c plus 1 is 0, and d equal to 2c. We are still short by one equation because we still need to find the value of a, c, and d. This can be done by using the energy conservation equation which demands that the total energy should be independent of time. Then we get another equation, a equal to d. So now with the four equations, we finally have a equal to minus 2 by 3, b is equal to 0, c equal to minus 2 by 3, minus 1 by 3, and d equal to minus 2 by 3. This is nothing but the x by t power 2/3 scaling because a is t minus 2 by 3. So basically we have recovered the x by t power 2/3 scaling, and we are also saying that with this set of initial conditions, the solution is unique. We have four equations and we have four unknowns. So this solution is unique. Another interesting question one can ask is, what about other initial conditions? In this initial condition, we have assumed V0 and E0 to be 0. We have only taken rho 0. The significance of this V0 and E0 comes in some problems like the Riemann problem, which has a single discontinuity in an otherwise piecewise constant initial condition. There you may have to use E0 and V0. If you just use rho 0, that you cannot reconstruct the solution. There, if we proceed by the same method, by substituting the scaling solutions into the hydrodynamic equations, we get a ballistic solution there. So we don't get x by t power minus 2/3, but we get x t power minus 1 there. So I just want to mention that these two are different solutions. Even ballistic solution is possible, and x by t power 2/3 scaling is possible in our system. Now this brings to Manas' question. We asked what happens to the dissipation terms. It turns out if we substitute the scaling,
just one question about this. So the thing is, you are trying to explain the scaling that you got for which dissipation term was important, right? Because otherwise the solution will blow up, right?
Yes.
but then to find out the scaling, you remove the dissipation term to do the scaling analysis, right?
Temporarily, yeah, temporarily. So what we have done is we have not added the dissipation term.
Okay.
But now what we are saying is now we want to see what happens if we add a dissipation term. Why are we right to say that I can neglect the dissipation term? And the answer is the dissipation terms under this scaling have a t power minus 1/3 dependence, which shows that in the long time limit it does not contribute. In the long time limit, the dissipation terms do not contribute to the solution, which is why I was right to neglect them. Had it been a t power 1/3 dependence or something like that, I could not have done this.
Right. But my question is, suppose you can neglect them because they don't matter. Yeah. But then suppose you don't have the dissipation term at all to begin with in your numerics.
Yeah.
Then you would never get all this scaling, right?
Yes.
So
we would never get all the scaling.
So the dissipation term is relevant to give the scaling, but it doesn't
contribute.
Sorry, why do you say that you won't get this scaling without dissipation?
Without the dissipation term, there is no solution at all, because numerically, at least we cannot do. But the scaling we can get it without the dissipation term analytically, because it's analytically.
In my mind, you're confusing two things. The fact that numerical solution doesn't exist is a statement that shocks are forming.
Yes.
That doesn't mean a solution doesn't exist.
Yes.
So then why can't I have a scale solution that decreases like t to the minus 2/3 even without dissipation?
That is because with the choice of a equal to minus 2/3 and all b equal to 0, we find that it is t power minus 1/3 dependence.
So Santhosh, did you try scaling x by root t? I mean, like if you look at in the diffusive scale, then I think the diffusion terms you cannot neglect and they will appear.
It's not collapsing. No, if I do x by root t, I find that this collapse doesn't happen. If the collapse does not happen, then we cannot say that it is x by root t scaling, right?
No. Okay, I'm not talking about the collapse, but suppose you want to look at your solutions at length scales, which scales as root t. So there probably the diffusion terms will appear, but
they don't satisfy. In that case, these Euler equations which you do, this t power a minus c plus d plus 1 will not go to 0. So this t term will be there. So this equation has a z dependence and a t dependence also. But we don't want that. We don't want t dependence. If we, let's say we do x by root t solution or some other solution, in these ODEs we have here, our purpose will not be satisfied. We don't want the t terms. We want the z terms. Z is x into t power a, it's true, but we want the combination of x and t only in the form of x into t power a and nothing else. Here, if you see the term 2 into t power a minus c plus d plus 1, that does not have an x term there. So you don't want the term there. You don't want the t term there. So the exponent has to be 0.
Yeah, I see. I mean, what I was trying to say that the diffusion term you can neglect, the contribution from the diffusion term you can neglect because you are looking at super diffusive length scales. That's super diffusive scales solutions, and there you see a collapse probably.
Yeah.
So Samriddhi has a question. He has written in the chat box. So he says, I can read it. Why can't you have numerical solutions even if SOC exists? There must be ways of doing this right.
Why can't they have numerical? Yeah. I will come back to that question in a little. In fact, I have it in the next slide. I'll come to that.
Sorry, Sandra, just if you go back to that plot once, I just so in that plot, here you had kappa and eta, right? So suppose I put kappa and eta to be 0, then so you're saying that you cannot really, you don't know how to.
I'll come to that in my next slide.
Okay.
Yeah. So let me just, before I do that, please give me an opportunity to just say what has been done so far. We've just tried to convert this PDEs in terms of x and t into a single variable z, x t power a. and we find that it is actually possible with the choices of this A, B, C, D. This is what we have done. So now what we have progressed is, first we started with Euler equation with no dissipation terms, and we have shocks and it's a blow up. So basically what happens is, if there is Euler equation with no dissipative terms, we get the three plots in the top panel. So at the long time we can see there is a shock and there's a blow up as well, and the solution we cannot the numerical integration doesn't progress beyond some time. What we have reduced the problem now by adding the dissipation terms is the bottom shown in the three panels at the bottom. We have seen that there are shocks here. One can notice that around t equal to 40 there is a shock front. There is a vertical line, but that is not blowing up. That is not blowing up as is shown in the panel above. Because of that reason, we are actually able to get these scaling solutions here. You can see that there are shocks here, but they're not blowing up. So basically, I hope it answers Manas' question. Basically, what we have reduced the problem, we have made it a simpler problem. We have converted this by adding dissipation term to this part.
Right.
The last part of my talk is,
but Santhosh, the top panel of your plot, let's say just before the blow up, let's say at t equal to maybe 30 or say up to t equal to 35, okay, something like that. Just before the blow up, you can still collapse the curve, is it?
No. This collapse happens at long times. No, collapse happens at around t equal to 100, 200 of that order. You can find a collapse. We can collapse, but it won't be very good fit.
Okay, so you needed to add the dissipation so that you can go to long enough times so that you can collapse it in future.
Yes. Now the final part of my talk is concentrated on to justify myself. I want to say I have made it easy for myself, but have I done a mistake in doing that? I want to investigate that now. The investigation is what actually happens to the system in the long time limit, and is this solution obtained in this way actually reliable?
Sorry, Santhosh,
in order
why are
to
there oscillations around the shock?
Why are the oscillations? Yeah, that is because I didn't add the Euler terms in the. I didn't add the dissipation term in the first three equations, first three plots.
Why should there be oscillations because of that? I mean, the oscillations must mean something, right? I mean, those oscillations are very clear, right?
Yes.
Let's say if you look at the plot of the velocity
for
red and green, those oscillations seem very clear. There must be a source for that, right?
That is due to shock formation.
This I don't understand. When shocks form, there will be oscillations necessarily?
Yeah, because we have a vertical line. So the moment a shock is formed, at the next instant of time, we start when we evolve the equation numerically without the dissipation terms. This will propagate. This does not happen if there are dissipation terms, which is why we did not observe it at the bottom panel.
Santhosh?
Yes.
This is, you see, I mean, for example, all I'm trying to say is that there could be a little more to it than just what you're saying. I mean, for example, if you use any of these schemes by Tadmor and others, probably Vishal knows them quite well, which are shock capturing schemes, right? People working for compressible flows have been using these for decades. You know, people doing polymer stuff where there are sharp gradients, etc. So capturing shocks correctly can't be a problem. I mean, it can't be a problem, right? There are various ways to do it.
But if that leads to a blow up, then it is a problem, right? If this increase with time, it's a problem, right?
What is increasing with time?
These oscillations.
So I'm saying, are those oscillations because you're not capturing the shocks correctly, or are those oscillations real? So if I think of various blow-up problems in Euler, in various classes of Euler, right? I mean, typically they blow up because some gradients are blowing up, right?
Yes.
In higher dimensions, at least. I mean, these oscillations, I mean, I still don't understand whether these oscillations are real or they are numerical
Yeah, they are, I think, numerical artifacts. So that's why, I mean, see, the adding dissipation is like a way of controlling the shocks.
Yeah, but I agree. I mean, this is routinely done in burgers, for example, right,
Right, yeah.
Abhishek?
The burgers also, you get exactly this kind of oscillations.
No, you don't get these oscillations.
No, if you don't, if you do it in a, like, it's a numerical artifact, of course. I mean, you can control it, of course, by improving, changing the
Okay, I mean, we can discuss this later, but
Can I just,
but there could be something in those oscillations. That's all I'm saying.
can I just point one thing?
Vishal, sorry.
Please.
Sorry, I was trying to just type it on chat, but I thought.
Yeah, no, I think
I've woken up my daughter.
Samriddhi, I think you're basically right. I just want to say one thing, which is numerical artifacts are as much a function of the particular numerical method.
Exactly. I mean,
they are not universal.
Yeah.
Yeah, it's not universal, of course.
This
and
is why...
secondly, if it's a numerical artifact which is coming from, let's say, some discretization, then Abhishek, I'm not even sure I'd call it an artifact, right? It would be based on the mathematics of the discretization, and then
right, yeah. So there must be some physics to the oscillations and all. So
then it's a very interesting problem. But to settle that, I think it would be good to use a real shock capturing scheme. That's all I'm saying. And rather than just say
right, yeah. No, so see, in this case, I mean, which Santhosh will present, you can actually more or less solve this exactly.
Yes, I'm about to.
So, and that you'll see that it compares, I mean, almost exactly with the adding dissipation term. So, in some sense, that's the.
Please look into McCormack method. It introduces dispersion.
Yeah, but sorry, but I'm saying there's probably, okay, we should move on probably, but there's
yes, I will finish it and I'm almost done.
Limit of viscosity going to 0 and viscosity equal to 0. That's the only point I'm making. And then, so I'm saying if you compare it with the inviscid solution, right, it may not, that is true, but that will probably be part of the story. That's all I'm saying. Yeah.
Yes. Just I'll come back to this, please. Just allow me to finish the last part. The last part is I want to see whether actually this is the right solution. Is this reliable solution by adding artificial dissipation? So what artificial dissipation started as a method to avoid the shocks, but I was able to avoid these blow-ups. But now the question is this reliable method, which is what we try to analyze now. One of the ways to check it with something. And the checking with something, we are checking it with the actual solution itself. We are checking with the actual scaling solution itself. So remember, in one of the previous slides I mentioned, these ODEs, PDEs have been converted to ODEs. Now we can solve these ODEs by RK4 method, traditional RK4 method. That can be done without the scaling terms. We can, in order to check whether the solution we obtain from this has a good match with the solution we obtain by adding the dissipation terms here. Dissipation terms have been added as for my convenience temporarily, but it should be able to explain the long-term behavior, whether we get the exact same solution or not, which is my final attempt. My final attempt is we have taken the rho, V, and T. We have taken temp T, slightly different format. We didn't take rho tilde, V tilde, and E tilde here. We have taken slightly different format, but it's essentially the same. With x by t power 2/3 scaling, we are just non-dimensionalizing it, and we are doing something else. Non-dimensionalizing it, and we are doing the same thing. We are solving the ODEs with these equations. L is a number. L is given by this number E naught t square by rho naught power 1 by 3. The aim is that x by L is dimensionless, so FGH are dimensionless. So we are trying to dimensionalize this, and RT is the position of the shock front. Is equal to ZF. ZF is a dimensionless, is a number. I'll come back to what is ZF later on. So basically what we are doing is we are trying to substitute these solutions, rho v t now, into the Euler equations, hoping that they give the long time limit solution. Why do I say that? Because long time limit, there is only z, x t power a, that is independent of time. So we can construct the shock. So basically, I'm trying to construct the shock solution. But in order to construct a shock solution, I have a ODE. But I also need the initial condition. I need a starting point to start from the shock. That is what I need. That I get it from Rankine-Huguenot conditions. To give a brief review of this, if a PD is in the flux conservative form del T psi plus del Rj equal to 0, integrating on both sides and using Leibniz rule, one can prove this J of R of T minus R dot T psi R1 to R2 is equal to 0. R is the position of the shock front, R2 is a point just after the shock front, and R1 is a point just before the shock front. I have taken in that way. And if I substitute Rankine-Huguenot conditions for three PDEs, I get these three equations where I have used f of f is f of zf for brevity. Mind you, I'll also tell you what is ZF in a moment. Please give me 5 minutes time. My time is up, but I'll be finishing in 5 minutes because of this internet connection. I apologize, but please give me 5 minutes. We have FG and we have converted this basically using Rankine-Huguenot conditions. We get FG and FF, GF and HF as the initial conditions. Initial conditions where initial conditions at the shock front. That is why I have integrated in such a way that R1 is just before the shock and R2 is just after the shock. So this ZF gives the position of the shock front. So if I solve these three equations, it turns out I was able to successfully solve. I got FF, GF and HF as the values. These are the values at the position of the shock front. So we have got the initial condition, we have got the initial ODE, we have got the initial value of FGAH, and now we just have to evolve. There is a small problem here. There is a ZF also here, because we have to also ZF, we integrate from where to where. That is another thing, and that is a not easy thing to say directly. However, we have energy conservation still into consideration. We have used energy conservation before, we are using it again now. The energy conservation says that the whole integral of that energy should be constant. In fact, it should be E naught. If we in terms of dimensionless variables, one gets integral 0 to ZF dz z square f into g square plus h is 1. So basically, we have to start with a random value of ZF, then take FF, GF, HF, solve the ODEs, then again check the energy conservation, whether it's 1 or not. If energy conservation is not 1, you have to take another ZF. So it's basically an iterative method to find ZF. In the end, we were able to get the right hand side, the error was like 10 power minus 2% or something, 1.0002 or something we were able to get. So it is good enough, satisfactory. So we started from the point at the correct shock front and we tried to go back. So what we did is we started from the position of the shock front, we tried to reconstruct it backwards. Now the question is, will that satisfy the hydrodynamic equation? Will it show the exact hydrodynamic scaling that I get in the long time limit? And the answer is yes. As you can see in these three plots, the red line is the hydrodynamic solution and the black dots is the scaling solution. The middle one is the velocity plot, which shows a very good agreement. The right and left show very good agreement, except at the center. There is a divergence in the center. So except this one point, we were able to give a good proof that yes, what we are doing is actually reliable. It's not merely a numerical artifact. But it would have also been better if we could also solve this problem at the origin. Why is there a divergence in the origin? And this could be seen in the scaling solution themselves. If you see the scalings, we see that at the middle point, actually these scalings are, they're not scaling actually, only at the middle. This V was scaling very well, which is why there was a good agreement. But rho tilde and T tilde, they're not scaling at the center, they're not collapsing at the center, which is the reason why we are getting a divergence here. This is what my talk is. So I just like to summarize it, my part of it. My part of it is just hydrodynamic equations. Euler, we started with Euler equations. We added extra term because there was a blow up. And then we found the x by t power 2/3 scaling. We confirmed it with analytically that it is actually x by 2/3 scaling. And now we also try to give an explanation that it's not just a fluke that we added the dissipation terms by hand. It's not merely a cook up. We have a proof. We have substantial proof to show that actually this scaling actually matches with the analytical scaling, which was found by using the Rankine-Huguenot conditions. This is my talk, and now the next part of the talk is deals with what is the consequence of this in the hard particle gas system, and what is the consequence of the alternate masses. And this next part of the talk also talks about why are we using the initial conditions, significance, what are the different types of initial conditions, and what kind of solutions do we get. And this talk will be presented by our friend Subhadip. And Subhadip, I hand over to you. Thank you for your time.
Yeah, thanks.
Subhadip, your
Yeah.
ball is in your court.
Can you hear me?
Yes.
Yes, yes.
Please stop sharing your screen, then I can share mine.
Okay, Subhadip, thank you very much. I stop.
So can you hear my slides?
Yeah, we can see.
Yeah.
Okay, okay. Okay, so Santhosh has discussed about the hydrodynamic part. So now we will, I will show some verification of the hydrodynamic from microscopic simulation for a particular model. So the TVNA solution for blast wave is an old solution for blast waves and verified by different experiments. However, a detailed comparison with a microscopic simulation is still lacking and has started very recently. So one of the first studies was done by these guys where they studied blast in a system of hard spheres like billiard balls, and initially all particles are at rest. So here is an collision cascade you can see. So the blue particles are at rest, and initially one central particle uh, has been excited, and they provide velocity to one single middle particle and see how the total number of moving particle uh, capital N function of t. So these red particles are the moving particles at time t. So they count the number of moving particle at time capital T and the total number of collisions at capital T and how they grow with time. And they found that from some scaling argument, they found this scaling for NT and this scaling this growing for CT, the number of collisions. And it can be seen that, so in earlier part of the talk, it goes as RT to the power D. So RT is the position of the shock, or that is this front is the shock front. So position of the shock front is R at time T. So if you do to the power D, D is the dimension here. So you can count the number of the moving particle. So, and they found, they verified the scaling argument from microscopic simulation. Here is the plot. Uh, so next, in this work, sorry. Oh. So next in this work, Barbier et al. Considered a hard particle gas in 2 dimension and 3 dimension. They used Euler equations as their hydrodynamic equation. They also they also considered hard sphere gas, and they also considered Euler equation as hydrodynamic equation. And the Euler equations contains there are 3 conservative equations. So for density, momentum, and energy, but they have an additional field, pressure. So there are 3 equations and 4 unknown fields. So one need an extra equation, which is the equation of state, by which one can express the pressure by other 3 fields. So they used one realistic relation between pressure, density, and temperature. This is called Henderson relation, where phi is the volume fraction, that is the volume of the all the particles, and divided by the total volume of the system. And they plotted 3 fields. One is theta temperature, U momentum, and N number density. and they divided it by the respective value at RH is the RH stands for Rankine-Hugonoid. So it is the value of that particular field at the shock front. So here, so they divided it by normalized it actually. So everything comes to this point. So they plotted, so the solid lines are the TVNA solution they found using this equation of state, and the points are from the microscopic simulation. And you can see they plotted for three ambient densities. So ambient density rho naught is the density of all the particles which are at rest, or which are at rest. So say at a low to medium ambient density, they found a more or less good agreement with the TVNS solution, which are the solid line, with the microscopic simulation, which are the points for three fields: temperature, momentum, and density. Okay. So this is the scaled distance from the shock center. So there are 2 points. One is shock center, that is the central point where the shock is applied, and one is the shock front. Okay, so lambda is a scale distance from the shock center, and they found good agreement in low ambient density, but for a higher ambient density, 0.4 and 0.5, you can see the analytical
So, sorry,
yeah.
can I ask a question? Maybe I missed it and you said it, but in the previous plot, and I guess in this plot as well, what are you plotting, sir? I didn't. Wait, lambda, and
Lambda
what is on the y-axis? What are the
y-axis? There are three fields. One is theta. Theta is the temperature field. U is the momentum field, and N is the number density field. And lambda is the position X, you can say, scaled position. So field is function of X and T. So they have plotted for particular only one time.
You said this is three-dimensional. When you were talking about it, you said this is. Sorry, I'm.
Yeah, so
I'm
that is why it is
something
R,
completely. I don't
X.
understand at all. This is three-dimensional. So what is lambda? I mean,
so lambda is
think
the.
of it as X.
Sorry, in one dimension, you can say lambda is.
No, you said this work was in 3 dimension. They consider 3-dimensional. That's what you told.
Yeah, so the 3 dimension, the shock front will be somehow like spherical, right? So the radius of that is the distance.
Okay.
So if you measure distance radially, that is r, small r, and if you divide it by the position of the shock front, capital R, then it is the scale distance from the shock center. That is lambda.
Okay.
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 Yeah,
so okay, in the larger ambient density rho naught, actually the hydrodynamic or the TVNA solution fails to describe the microscopic result in near the shock front. This is the shock front, and also at low lambda, that is near the shock center. Okay, in both region.
Hello.
Yeah.
So is it that at very low lambda hydrodynamic equations breaks, and at high lambda at high density your equation of state description breaks?
Yeah, they didn't conclude about that. Yeah, maybe the equation state is a very important function here. Maybe that is the reason. There may be several more reasons. I will come to it in the next slide. Actually, there may be, in the next work by R. Rajesh, they also verified the same thing. I will go. They claimed that equation state is one important thing, very important thing. Along with that, there are many more approximations of local equilibrium, and there are also you can add an dissipative term or heat conduction term. If you
my point is near the shock, since the space derivatives are very fast, very large, that means things are changing very fast over space. So I would say because of the continuity equation, they were also changing very fast in time. And
yes.
there using equation of state, I do not find it very justified to use equation of state, at least at that region.
maybe you are right. I don't know.
Okay, please go ahead.
Okay. So the problem is the hydrodynamics deviates from the simulation significantly at high ambient density, and also they present result for a single time, that is maybe they have not reached the scaling limit. So that is one problem with their work. And they also found a similar way to calculate uh, those fields uh, for the inelastic hard sphere, where energy dissipates when they collide, and they added an extra energy dissipation term in the energy equation, Euler energy equation, and they found a good, more or less good agreement in the inelastic hard spheres. Okay, so in this work, Joy and Rajesh and others, and they also used hard sphere gas, and also they considered Euler equations at hydrodynamic description, but they used equation of state, the ideal gas equation of state, and they tried to verify the TVNS solution from with the microscopic simulation. And you can see this black solid line is the TVNS solution. So they calculated for two ambient density 0.1 and 0.4. They scales for different time. In previous case, in Barbier case, they plotted for only one time, but in Rajesh plotted for 4-5 times. So this scales independently by t to the power 2/3, that is the TVNS scaling. But the problem is the scaling function does not agree with the TVNS solution, the black line, and also the scaling function they found numerically depends on the ambient density. So in this TVNS solution, it is independent of the ambient density. So you can see this for this velocity plot, this is significant. I mean, very far away from the simulation result. And they also plotted temperature and pressure, and none of them agree with the simulation. Okay.
Sorry, what's the black line?
Black line is the TVNS hydrodynamic solution, considering the equation of state, ideal gas equation of
for
state.
for which the velocity does not go to 0 as r goes to 0? I don't understand.
Yes.
Sorry, what does that mean? Can you
explain? Yeah. What does that mean? I don't know what does it mean. Maybe.
Okay.
Yeah,
fine. Anyway, move on.
Yeah, that is very original. Yeah. Okay, so what they tried to change is that they replace the equation of state from ideal gas equation state to a virial equation of state, which is more realistic for this type of system. And they this virial sum n, they used different n is equal to 2 to n is equal to 10. So, and plotted for the left hand side, all 4 plots is for rho naught is equal to 0.1, the ambient density. So, and the right hand side, all 4 plots are for ambient density 0.4. And again, the black line is the TVNS solution for the equation of state, ideal gas equation of state. And for virial equation of state, and this equation, the TVNS or hydrodynamic results converge at higher n. But one thing they achieved is that now the scaling solution or the hydrodynamic solution depends on the ambient density. You can see the ambient, the scaling, hydrodynamic solution is different for different rho naught. Okay, but still they cannot capture the simulation result. Okay, they are far away from the simulation result. So that is the
sorry, one more question, just to make sure I understand what you're trying to say here. I mean, of course, you're trying to just present their paper, but just to understand, when you say simulations, you mean you take particles and
Yeah,
some
exactly.
appropriate
Microscopic
dynamics of
simulation.
those
Yeah,
particles. That's what you
molecular
mean by
dynamics.
simulations, right?
Exactly, exactly.
And when you say hydrodynamics, are you
Hy-
saying numerical solutions of the hydrodynamic equations, or actual there are some possible analytical forms that they use?
So in our works, Santhosh has presented both. I mean
No, but here I'm saying the
okay,
result
in
that
this
you're
work,
presenting right now.
the analytical, I think it is. I mean, not
Yeah, it is
numerical.
like you have to numerically solve some ODEs, but so it's almost analytical
Yeah.
with the
I see.
Rankin-Hubernet boundary conditions.
Okay.
Okay. So our system. Can you see the heading? Or
Yeah.
Yeah.
so yeah. So our system is a one-dimensional alternate mass hard particle gas. So we consider n hard point particles in 1D box of system size L minus L by 2 to L by 2. The particles are ordered in this way, and as their interaction is hardcore kind of nature, so the interaction potential is infinity when they try to cross each other, and otherwise it is zero. So this is the interaction potential, and one can write down the Hamiltonian in this way. Okay, so they collide via perfectly elastic collisions which conserve energy and momentum, and after a collision the velocity of two particles can be written in by these equations. Okay, so you can see that for equal mass, if you put m1 and m2 is equal to m, so v1 prime will be v2 and v2 prime will be v1. So they exchange velocity, and effectively they become non-interacting. And this is for equal mass case, this is an integrable model. And we consider here alternate mass. So we consider like odd position. In odd position there are the mass is 1, and the even position it is 2, where the effective mass mu is equal to m1 plus m2 by 2, which is 1.5 in our system. So this alternate mass case is non-integrable system. Okay, so in alternate mass, it is an interesting system because first of all it is a non-integrable model, and it is a prototypical model for ideal gas. So that is why we know the what is the equilibrium state for this system. So the equation of state is exactly known, unlike the hard sphere gas in the higher dimension I discussed in earlier works. Okay, and they used virial approximated equation of state, but we know what is the equation of state exactly. So from that equation of state, using in the Euler equations, one can obtain the TVNA solution exactly for this particular model. Okay, so we use event driven molecular dynamics simulation for this microscopic simulation. To do that, we order the particles in position, and once they are ordered, they cannot cross each other as they are hardcore particle, and we find the shortest time of collision. Then particles which are not colliding will move ballistically, and this will save a lot of computation time. So here I made a movie. So each color are for a different mass. You can see. So I should have made it for this Hawk problem, but I have movie for where all the particles are at left hand side and they go to steady state. So you can see the interaction. They collide. Okay. So this is as I mentioned that it is an interesting system, alternate mass hard particle gas, and many exciting works has been done for this system, such as breakdown of a Fourier law of heat conduction in one dimension, A remarkable finding is that the thermal conductivity kappa diverges with system size as kappa goes as L to the power 1/3, and this were discussed in these references. And in this next work, in these works, some theoretical understanding has been achieved to predict equilibrium dynamical correlations in details using a fluctuating hydrodynamics for some anharmonic chains, and those predictions are verified in these works from microscopic simulation of alternate mass hard particle gas. Okay, and in this work, as already discussed by Santhosh, so in this work, the author solved the Riemann problem for Euler equations. The Riemann problem is you have an infinite system, and all the profiles are initially like step initial conditions. So the profiles initially are step function. Okay. So and they compare the time evolution for this problem for density rho, velocity v, and temperature T, and these profiles with microscopic simulation, and they compared, and there they found that the shock front, that is the step part, which we call the shock front, and the profile scales ballistically, which already discussed by Santhosh. So now we now define three fields. One is density field, another is momentum field, and third one is the energy field given by these three equations. So to calculate them, you need to grid the system in small partitions, and need to calculate density, momentum in each partition, and you take average over initial condition. Then you will find these three fields, and you can define an additional field temperature, which can be calculated from the velocity fluctuation, and this is that 2 mu in epsilon. Epsilon is the internal energy. So the equation of state is given by this P is equal to 2 rho E, or P is equal to rho T by mu. So these are the fields we are going to use or calculate. So we calculate these three fields, or evolution of these three fields, rho, v, and t. So to do that, we start from an initial condition where.
Sorry, since I don't know enough about the field, just in the previous slide.
Yeah.
Maybe you mentioned this. I don't know if I missed it, but this. These pointy brackets, what that's average over what?
Initial condition, initial configurations, better to say.
So you take this with a variety of initial conditions, and these pointy brackets are basically average over those initial conditions.
Exactly.
Okay, fine. Yeah.
So we start from, and this we call Gaussian initial condition, because finally the energy will look like this Gaussian picture profile. So to do that, we distribute n particles in system minus L by 2 to L by 2 uniformly. Okay. Now we sort them in order, and that is order them in position as I is equal to minus n by 2 plus 1 to n by 2. Okay. So after distributing uniformly, we order them in position. Then we assign alternate mass to them, m1 and m2, m1 and m2. Then we assign velocities to nc number of particles. So nc is the nc number of particles who are at the central region. Okay. So the tag of those particles, those nc particles, the tag is minus nc by 2 plus 1 to nc by 2. Okay. So, and we provide the velocities, and we draw the velocities from Maxwell distribution with mean 0. The distribution is given by this quantity. At T0 is the E0 by NC, where E0 is the total energy of the blast. Okay. So you can see so the red particles are not the central. This is the whole. So here I show 4 configurations. Okay, 4 configurations. In the first configuration, you can see that the NC, as after distributing, we sort the particles in position. So it is not necessary that all the NC particles will be in the central region of with NC. So we consider n is equal to L. So the central region will also be minus NC by 2 from NC by 2. And the number of central particle is also NC. But it is not necessary that always the central particle will be in the central box. You can see these or these or or all the particles in the central box. So various configurations are possible. So that is why if one can calculate what will be the initial distribution. So the initial density field will obviously, as we distributed uniformly, it will be flat, given by this mu. So we took n is equal to L. So this is given by the effective mass mu, which is m1 plus m2 by 2, which is rho naught or ambient density. And the velocity is 0, as the mean of this Maxwell distribution is 0. The velocity field initially is 0. And due to this condition, the energy field initially will look like this Gaussian profile, where the sigma square width will depend on the system size. Okay. So for this initial condition in the alternate mass had particle gas, we simulate from event-driven molecular dynamics simulation and plot the 3 fields. One is rho density, second is the mod of the velocity, and third one is the temperature as a function of x and t, the spatiotemporal evolution. So you can see, so as time goes, the density decreases at middle and near the shock center. We call this part is shock center. So the density decreases at the shock center as time goes. And you can see.
Sorry, just one question. Maybe you mentioned it. So the particles can reflect off the boundary, right? It's a finite box, right?
Yeah, finite box, but to do simulation we use finite blocks. But actually we are looking at long before they reach the boundary. So we are interested in that regime where they do not reach the boundary.
I see. Because if you wait long enough, then this should just thermalize, right?
They thermalize, yeah, definitely.
Okay. So your timings are much smaller than that. Okay, fine.
Yes, so that they do not reach boundary.
Sure, thanks.
Okay. So, yeah, you can see the growth is not ballistic. This is half ballistic. This is t versus x. So if you feed this, you will see t will go as x to the power 3 by 2. That is, x will go as t to the power 2 by 3. Okay. So both density and velocity has a peak near the shock front. These two are shock front and this is the shock center. But the temperature profile has an additional peak in the shock center. Okay, that is the observation. So this simulation was done for n is equal to L is equal to 18,000 and the initial blast energy was taken 32. So here are the profiles. Sorry, yeah.
How did you measure temperature? I mean, how did you numerically find it?
I measure from velocity fluctuation. So we calculate average velocity and velocity square average. Okay.
Okay.
And from that difference, we calculate the temperature profile.
Okay.
So we present the profiles at large time. 4 times we present here: 5,000, 10,000, 20,000, and 40,000. You can see the density decreases in the shock center as time goes. This is the velocity profile, and this is the temperature. We have one additional peak in the shock center here. Okay. So these are the plots at large time. Now we try to scale those with x and t, and you can see that the scales as expected from the TVNS solution, the scaling is x by t to the power 2/3 for all of them. They scales almost in most of the space except in this region and this region. So near the shock front, this is the shock front region, and near the shock center, they do not scale well. So you can see that they are still converging. So the convergence is very slow. So we need to go for long time to get a good convergence. And we also plot this dotted line is the TVNS solution, which discussed by Santhosh earlier. So this is the TVNS solution, and this is the lines are the microscopic simulation result for these three profiles, three fields. Okay, so that scaled fields are defined in this way, this three way. Okay, so you can see the TVNS solution also captures in most of the places inside the blast, but it cannot capture the simulation result near the shock front and also in the shock center here also near the shock center and the shock front. So the interesting thing, we do not see any shock. That is the most interesting thing here. So the profiles are smooth. Okay, now we compare all three results. So the first one is the hydrodynamic result. So hydrodynamic result is done by solving the partial differential equation. So discussed initially by Santhosh, and this scaling solution is the exact result by a TVNS solution, that is solving the ODE, and this line is the microscopic result. So again, the scaling functions are given by these three equations, and scaling fields are given by these three equations, and they do not agree near the shock front and near the shock center.
Sorry, just one question. So in the microscopic calculation, you check that even by increasing n, basically there is no it doesn't become sharper, right?
No, it doesn't. No.
Okay. So basically,
increasing n make it. I mean, this convergence will be good if we increase the system size and n,
right.
L and n. But no, there is no shock.
Okay. And what was the value of n used here?
Yeah, this one. N is equal to L is equal to 8.
Okay.
8,000 and P naught is equal to 32.
Thanks.
Okay, so we can also define the empirical fields defined in this way. This is the same way. Only difference is that we do not take the average over initial configuration. The rest of the part is same. So you grid the system, count the number of particles, and count the momentum, count the total energy in each grid, and that will give you the empirical field. We do not do average over initial configuration here. So we want to compare these empirical fields with the marginal field. Marginal means earlier we discussed, that is average over initial configuration. So here also we did this on L is equal to N is equal to 18,000. And you can see the dotted lines are the marginal or average profile, and the solid lines are the empirical fields at different times. And you can see that in a total energy, so we compared for two initial configuration. One is one initial configuration, this is the second. Oh, this is also one. No, this is two. So initial configuration 2. So it is expected that for a particular initial configuration, it may not be, E0 may not be 32 always. So if you do average over initial configuration, the average blast energy will be 32. So at long time, and the profile looks similar. You can see the temperature profile and all. Okay. So as here, the average initial blast energy is 32. This is lesser than that. That is why the empirical profile is lower than the average profile. Because for average it is 32. This is 24.4. Okay, so we compare with another initial condition, which is box initial condition. In this initial condition, we consider uh, again a system minus L by 2 to L by 2. Then, yeah.
No, I'm saying maybe it's quite late, so maybe you can try to wrap up.
Okay, yeah. So box initial condition, we break the system in 3 parts, and we distribute particles independently in 3 parts, such that the initial condition looks like this. The density profile is flat, velocity profile is also flat and 0, but the energy profile is like box. And we compare the corresponding Gaussian profile and the box profile. So you can see at later time, they agree. So it will be clear from this plot, this temperature plot. This is the box profile, this is the Gaussian, these are points. And you can see at large time, the profile does not depend on the structure of the profile. It only depends on the E0, that is the blast energy, and rho naught, the ambient energy. That is all, which is expected from the TVNS solution. And we also calculate for equal mass case. Equal mass case is very trivial. They are non-interacting, and that is why they can be calculated exactly. So we calculate them analytically. The lines are the analytical result at different time, and points are the microscopic simulation result. And interestingly, they are the scaling is ballistic here, as they do not interact. So line is again the analytic.
How
Right?
does
Okay.
no?
So summary. Yeah.
Okay, so
Hello.
if you plot the TV in a solution in the equal mass case, how bad are they?
Equal mass case TVNS solution.
Mm.
The TVNS solution will be same, right? And you just
With
need to
the
put mu.
see,
The same equation of state, same Euler equations.
But the TVNS solution is derived with the different scaling assumption. So
Yeah. That is true. Yeah.
here it's ballistic scaling. So
Ballistic scaling.
they're completely different.
yes.
So to summarize, almost the summary part already have done by Santhosh. So a detailed comparison between hydrodynamic Euler equation and microscopic simulation is made in the context of evolution of blast wave. So we consider alternate mass particle gas for our model. So partial agreement between TVNS solution and microscopic simulation. The disagreement is near the shock front and near the shock center, and the inclusion of dissipative terms helps us to do the hydrodynamic numerics easily, but it does not affect at long time, and it converts to the TVNS solution at long time. So possible reason behind disagreement between microscopic result and the hydrodynamic solution is that the convergence I already discussed. The convergence is very slow, so we need to go at large system and large number of particles, and also large time to see they will go close to the hydrodynamic prediction. And that we use in the hydrodynamic equation the Fourier heat conduction, which fails in the one dimension. So that may be one reason. So that's all. Thank you.
I apologize for the causing delay. I made Subhadip talk soon and all, but it's because of my net connection.
Yeah, it's fine. It's fine.
Thank you, Subhadip. Does anyone have questions? Okay, if no one has questions, then let's thank Subhadip and Santhosh again.